Good afternoon, students.
Good afternoon, sir.
Okay, just give me 2 minutes, okay? 2 to 5 minutes, just wait. Okay, I am back. Just a minute. Are you able to see the screen?
Yes, sir.
Yes, sir, it is
Okay.
visible.
Yes, yes, fine. Okay. So sound is okay, or you are getting some extra sound, noise or something? Sound is fine, or some disturbance you are getting?
Some disturbance, sir.
Sir,
Just a minute.
something
Some
is blowing,
disturbance, sir.
air
Yeah,
blowing, sir.
yeah, okay.
Sir, something is
Fan.
blue.
Okay. Yeah, now it's fine. Actually, due to fan, now it's fine. So we are going to start new chapters, that is work energy, and that is under kinetics of particle. Now, so we have discussed before that Newton's second law, F equal to ma, for different types of problems, and we have shown some instantaneous relationship between net force acting on a particle and resulting some accelerations. Now we have to determine the change in velocity or corresponding displacement of the particle. Then we can integrate the computed accelerations by using appropriate kinematic equations. Now, when we are solving some problems when velocity change are involved, one way we can do this, that our target is to see the cumulative effect of the unbalanced force acting on a particle. Then either we can, in two ways we can solve. We can do integration of the force with respect to displacement. So integration of force with respect to displacement, or maybe integration of force with respect to time. Integration of force with respect to time. Okay. So if you are doing so, first case, this is relates to work and energy, and second, this one, this is relates to impulse and momentum. Impulse and momentum. So this is work and energy, and this is impulse and momentum. So today we are going to cover this part, work and energy. Now, definition of the work was everything you know before also. This is some force is been acting on the particle. Due to this force, particle will move along this directions, and this is the position vector r plus dr. This is dr is the displacement, and it is making some alpha, angle alpha. Particle is moving from A to A prime. Okay, and this position vector are with respect to point O. Now particle is moving A to A prime due to application of the force F, and it is making some angle alpha. Now, definition of the work was something that it is dot product of a force applied dot product and change in position vector. Change in position vector we call displacement. Okay. Now, as this is dot product, is scalar. Okay, this is the scalar quantity. Now, two way people can think like, as this is dot product, so somebody can get from this that that magnitude wise, this is magnitude wise, it is F, and if dr equal to ds, then it is F multiplied by ds multiplied by cosine alpha. So F dot dr equal to 2, we can write that F cosine alpha component of F along this displacement multiplied by ds, or force multiplied by ds cosine alpha. So either we can take force component along ds or ds component along the force directions, along the force direction. So this is the force. We can decompose it into two case, Fn, Ft tangential, and one is normal. So normal and normal with respect to what? The displacement. So normal one, as this angle is 90°, it will not do any work. But which one along the tangent, it will do the work. So it is f cosine alpha multiplied by ds. Or maybe we can consider let's have ds component along the force f, along the direction of force f. So f multiplied by ds cosine alpha. Whatever the way we will do, we will get this one. Now somebody can have these equations change in du, that is the change in work done, that is ft multiplied by ds. Okay. Now two component f is having now vectorically, one is ft, one is fn. Okay. This ft is doing the work. Ft is the direction of the displacement, and if the displacement and f are both in the same direction, then it is positive. But if it is in reverse directions, force you have applied in one directions, but displacement is in reverse directions, then it will be negative. And this Ft is known as active force. On the other hand, active force which is doing the work, other one Fn is called reactive force, which will not do any work. So active force and reactive force. Now unit generally we write, as this is Newton multiplied by say meter, we write in joule. Why? This is our usual practice to write in joule to differentiate between the moment or bending moment or twisting moment or torque. There also we have received the unit, we have seen that the unit was Newton meter. So here we will usually write in terms of joule to represent the work done. Now when we are doing calculation of work done in three-dimensional cases, so it is moving from point 1 to point 2. So it is f dot product of f dot dr. So component wise, fx dx, fy dy, fz dz. If we have only one direction, then f multiplied by x. Okay. Or sometimes we can write in terms of ft. It is ft multiplied by ds. S1 to S2. So position 1 to position 2. Now here it has been shown, this is the ft. You have to be careful that we have never using fn, that is reactive force, that is not doing any work. Okay. That is the reactive force. So like when we are walking, then with respect to gravity in that directions, so the gravity force is acting in that directions, and we are walking in a horizontal plane in other directions, no work, correct? Because then our self weight basically will be the reactive force. So now be careful, it is ft and it is s. S is the displacement. There are 2 points, say S1 and S2. Okay. Take one small step. This is representing ds. Then your work done will be ft multiplied by ds. Now you do the integrations to get u 1 to 2, sorry, or S1 to S2 ft ds. That one will use. Okay. Now this is one classic example, that this is one body, its weight is say mg, and it is moving. This is x directions, y direction, moving from this point to this point. Sorry, this point to this point. This is A prime, this is A, this is B to B prime. Okay, and distance traveled is L. It is making some angle alpha. This is the dr. This is the P. So this is the scenario when we have introduced some angle alpha. Some angle alpha. So work done associated with a constant external force. When we have force is constant, F is constant. So F can be come out from the integration point by definitions. U12 is F dot dr. Okay, 1 to 2. So it is 1 to 2. We have applied P. So it is here P cosine alpha, and this is P sine alpha. So it will be P cosine alpha multiplied by I plus P sine alpha multiplied by J dot product dx multiplied by I. So dx is the component multiplied by I to show the vector. Here P cosine alpha, P sine alpha, this has been multiplied with I, and that is J. Considering in A directions, unit vector is I. Okay, as this is dot product, so this J and I, that dot product will be 0. So finally we will get P cosine alpha multiplied by dx. Here it is x1 to x2. So P cosine alpha x2 minus x1. Correct? From the integration, that is PL cosine alpha, or somebody can write this way, P cosine alpha multiplied by L simply. Okay. Now when this alpha, when is alpha is ranging from 0 to 90 degree, so it is ranging 0 to 90 degree, one case, or maybe alpha is acting greater than 90 degree, less than 270 degree. So when this is happening, this alpha is less than 90 degree. That means the directions we are applying the force, in the same directions displacement will happen. So work done will be positive. Work done will be positive. Okay. But when alpha is between 90 to 270 degree, so the directions you have applied the force in reverse directions, the particle will, or the body will move. Okay, so it will be negative work. It will be negative work. So it is negative. This is positive. But Fn component, the force component P sine alpha, normal to the displacement, will does not work. So it is reactive force. Now this is the work associated with a constant external force. If it is not constant, then it will be integration form. Ft is given, say for example, Ft is given in the form of, it is function of some position vector S or displacement. Then we can do the integration to get the work done. So this work done, WD, work done with force, with constant force, we told here, it may be with spring force. It may be with spring force, or it may be with its self weight. With self weight. Now IIEST. Constant force we have understood. Now work done with associated with a spring. Now very nice thing for the spring, if you consider this is the spring, this is the undeformed conditions. T equal to 0, x equal to 0. And this is the deformed conditions, some instant, t equal to t, x equal to x. So once we move from this to this point, that means we have stressed, or maybe we can compress also. Then what is the force will act here? The spring will try to get it back to the original conditions. So spring force will be kx. spring force will be kx. So K was basically P by delta or F by delta, force required to produce unit displacement. So F will be K multiplied by delta. Here it is X. That's why it is A spring constant multiplied by X. I told before also, in general term, K is the stiffness. Here stiffness of the spring. And this is the directions of your position vector change. So the directions force here kx, spring, only spring force I am talking about, and the displacement they are in reverse directions. So it is negative. It will be negative work done. Work done associated with spring, work done associated with spring is negative. Why? Because the directions it will move, displacement will, the direction it will move, spring force will act in the reverse directions. Now you take another examples. Maybe instead of these directions, we are moving these directions. This is the movement. This is the dr. In that case, what will happen? Spring force will act these directions. So both way it is something, when we have started with the original positions, undeformed positions, always your movement, position vector change will be opposite to the spring force. So both case work done will be negative one. Now if somebody can write that this is the x directions and this is the force required to stress or compress the spring, relationship just like y equal to mx, where c equal to 0, straight line. Okay, this m represent the stiffness here k, this is x, and y represent f. Okay, now if somebody want to move from this to this place, work done will be, as I told, it is minus x1 to x2 f dx. Okay, if somebody write f equal to kx equal to minus x1 to x2 kx dx. Spring constant k is constant, okay, is not vary. So it is x square by 2. Limit is x1 to x2, correct? So it will be minus half of k multiplied by x2 minus x1 square. So this is associated with negative sign. Okay, and that is nothing but area of this curve, area under this curve. That is the value here, what we are talking about. That is the work done. So in other way also we can show. One way we have done integration, but simply we can write this way also. That is this k, the rectangular area will be, sorry, it is f, this is f multiplied by x2 minus x1 plus this area, half f multiplied by x2 minus, this is, yes, half f x2 minus x1, x2 minus, so this is straightforward, f multiplied by, this is the f basically, but one issue here, that is this value is changing, or I should write here, this is f1, write f1, and this is you write f2. Here it is f1, it is f2. What is f1? F1 basically kx1. F1 here it is kx1. This is f1. So this is f2. Okay. Now it is or it is f prime. I should write here, it is f prime. But f prime we should take care like this. This is f2 minus f1. Because this distance, this length is f2 prime minus f1. Or simply I can write this way, kx2 minus kx1. This is kx2, here kx1. Now if somebody do this calculations, you will be getting this relationship, half x2 square minus x1 square. So both way people can do. One is you have two area, a1, a2. This is instead of f1 you can write kx1, and this is kx2. Now you can calculate this area, kx1 multiplied by x2 minus x1 plus half x2 minus x1 multiplied by this height is kx2 minus kx1. You will get this relationship. Whatever the way you want, you can show. I believe this is well known and you can utilize this. But this has come from the integration. This relationship is known to you since I think 8th standard or 9th standard, but that has come from the integration. That work done has come from the integrations. And this is negative sign because the spring force acting in a direction which is opposite to the displacement or change in position vector, because the spring has started from the undeformed conditions, unstressed conditions. Okay, it's done. Now work associated with the weight. Okay, so now if I want to move from this point to this point, point 1 to point 2, okay, and it is some arbitrary path, it is following some arbitrary path, okay, but whatever the path, it is independent of the path. It will only, if you take this way, that f dot r work done for point 1 and 2 minus mg. Why minus mg? Work done. Why it? Because when you are moving against the gravity, it is negative work, so it is minus mg. Okay, you are moving against gravity, it is minus mg. So this is I, this is j unit vector along x and y respectively. So mg multiplied by unit vector dot dxi plus dyi, because movement is in both directions, dxi, dx and dy. Okay, it is both directions movement, dx and dy. So if we multiplied with I, here j, as this is dot product, so this j multiply dot I will be 0, j will remain, and that will be minus mg integration over minus y to y, y1 to y2, y1 to y2 dy. So it will come with the minus sign. Okay, with the minus sign. Why it is minus sign? Work done is against the gravity. It is the force is acting toward the center of the gravity, but the displacement is happening, that is not towards the center of gravity, it is away from the center of gravity. So that relationship can be used. You know this before also. Okay, now one curvilinear motion example we can take. This is the path of the particle. It is moving following some arbitrary path, and at this point mass is m of the particle, some position vector is r, change in this position vector is along t directions. This is the normal, so t and n, this is 90 degree. So this is the normal directions, this is tangential direction. Be careful, fn, that part will be 0, because particle is moving in a tangential direction. Instantaneous directions we are considering for the car path. So what we will do, u12 will be 1 to 2 f dot dr. So s1 to s2 ft ds. So along dr it is ds. So ft ds. Okay. Now if I replace that f equal to ma, f equal to ma, force equal to mass multiplied by acceleration. Definitely this acceleration basically at, okay, and this force is basically ft. If I utilize this, then these expressions with f I can replace ma dot dr. Okay, fine. Now this A basically A dot dr is nothing but ATDS. Okay, AT is the tangential accelerations. ATDS. Okay, now we know this ATDS can be written as VDV. ATDS can be written as VDV. So we will replace this U12 equal to this M. Here it was here M A dr. So M is common. A dr will be A T ds will be V dv. So it is M V dv. If I do like this, so limit of integration will be V1 to V2. V1 to V2. Okay. Now that is nothing but if you do the integration half M V2 square minus V1 square. Okay. Change in and half mv square is kinetic energy, say change in kinetic energy. Okay, change in kinetic energy. That work done is associated here due to the curvilinear motions. Now here kinetic energy has been written as T. Okay, we will write Ke equal to T. So you recall that here it is this book represents kinetic energy as a T. T is the kinetic energy, not torque, not tension. Okay, you can write in exam T also. T equal to half mv square. Okay, now using this expression you have to be careful. It has been told that it is Newton meter for joule and foot pound for US customary units. Okay, and kinetic energy is always positive as it is associated with v square. V may be negative, but energy will be positive and scalar quantity. Now 3.13 expression, let me check. 12. Yes, this is the 3.13 expression. U12 equal to half m v2 square minus v1 square. Okay, somebody can write this one half m v2 square, this one half m v1 square or delta t. This is the change in kinetic energy. So this equation is known as work energy equations. This is known as work energy equations. What? Here in curvilinear motion, I have shown that this is the work done. By definition, work done was F dot dr. That is nothing but here change in kinetic energy. Okay, work done is nothing but change in kinetic energy. So U12, this work done is nothing but change in kinetic energy. That relationship is called work energy equations. Okay, and that is you are doing some. The equation states that total work done by all forces acting on a particle as it moves from point 1 to 2 is equal to the change of kinetic energy of the particle. Okay. Now you have to recall, although T is always positive. Okay, kinetic energy. T is kinetic energy, always positive. But the change in kinetic energy may be negative. If T2 is higher than T1, then change in kinetic energy may be negative. That means work done can be positive and negative. When it is positive, that force applied and displacement both are in the same directions, then positive. If both are in the opposite directions, then it is negative. Okay. Now the same equation we can write that T1 plus U12 equal to T2, or maybe you try to recall work done equal to Ke2 minus kinetic energy 1. If you are comfortable with this instead of T, I have no issue. That expression is also fine. Now the advantage of this work energy method is we don't need to go into details of knowing the accelerations, knowing the forces, but all details we don't want. We only want initial state and final state. Velocity, if you know initial state, what is that kinetic energy, final state, what is the kinetic energy, what is the difference, that will be work done on the system. Yes, work done on the system. Why system? We are considering so many say, objects or particles as a system. We can say that way also. This is work done on the system. Okay, you are doing some work externally. Externally, you are giving some work. That is, if you add some work to the system, then the kinetic energy will increase. That means Ke2 will be higher than Ke1. So, and you don't need to go into details into what the accelerations, what time, okay, what directions, nothing. As this is scalar quantity, work energy principle is very simple. It is advantageous because to calculate what is the work done, we have to just find the change of kinetic energy for the two systems, 2 points, say, or two time step 1 and time step 2, and that is been explained here. Okay, now when we are talking about power is time rate of doing work. So P equal to du dt, you know this one. Okay, and it is scalar quantity. Work done itself is scalar quantity. Okay, so it is f dot dr dt, f dot dr dt. Here it is vector f dot dr dt or dr dt. Okay, and dr dt is nothing but velocity. Dr dt is nothing but instantaneous velocity. So it is f dot velocity. So power equal to f dot velocity. Okay, so you know the Newton is unit here, it Newton, then it Newton meter per second. That will be the power, or people write joule per second. Yes, so joule per second we will write, and there are some relationship. So what we understood, this joule per second also, you know, it is watt, nothing but 1 watt. So this is the power. Capacity of any machines is measured by the time rate at which it can do the work, or it can deliver any energy, deliver energy from one side to other side. Okay, and that's all. And when we are considering about the efficiency, that is power input by power output, power input by power output by power input, and it's supposed to be less than 1. Input supposed to be higher than the output. Now there could be sometimes many equipments. Basically, there are many types of loss we call energy loss. Okay, energy loss, how it is loss, it may be in terms of mechanical friction, in terms of sound, in terms of heat generations. Okay, maybe in terms of electrical and thermal energy loss. Okay, so if we consider that efficiency, electrical efficiency, say EE is the electrical efficiency, and maybe ET is thermal efficiency. There could be many types of efficiency. In higher class you will come to know. Okay, maybe thermal efficiency. Okay, one is EM, mechanical efficiency. Okay, due to friction, mechanical efficiency. Then overall E would be EM multiplied by ET multiplied by EE, or many more. Sometimes it has been told in some problems, you'll know in higher classes application, there are many types of efficiency loss due to, here I am showing 3, it can be more different types of losses of the one, say, power plant, okay, one automobile systems, one gearbox systems. Then what we supposed to do to calculate the overall efficiency, we have to multiply by each and every uh, 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 efficiencies. Okay, now let's take one examples that calculate the velocity v. We have to calculate velocity of the v of 50 kg crate. This is the 50 kg crate. When it reaches the bottom of the chute at B, it is moving basically from A to B. Okay, if the initial velocity v is 1 equal to 4 meter per second. Okay, if it is given a initial velocity that is down, so initially it is important. This is v1. It is along the down. The coefficient of kinetic friction mu k 0.3. Okay, we have to calculate the velocity. Now we have to be very careful to solve this problem. How? Mass is given, so W equal to mg, that is acting here. So there will be some reaction force. So R equal to mu k multiplied by R is given here. R will be this W. Just a minute. This is W equal to this kg. Then one step. It is one step by step. I'll move. It is better. So this is. Let me. I can use the calculator. Just wait. 50 multiplied by. Book has some step jump. It is giving issues. 50 multiplied by 9.81. Okay. That is 50 multiplied by 9.81. This is 490.5 Newton. This is the W acting here. Okay. Next is we know only this value. Then this is 490.5 Newton. This is N. This is mu Kn. Okay. N mu Kn and 15 degree, correct? This is 15 degree. Okay. Now this is alpha equal to 15 degree. So this is also, if it is 15 degree, this will be alpha, this also will be alpha. Okay. Now this is x, this is y. Summation Fy equal to 0. No acceleration along that directions. Okay. So N equal to 490.5 cosine alpha, cosine 15 degree multiplied by cosine 15 degree. That is 474 N. Okay. So initially you write N, then you calculate N equal to 474 N. Okay. Now if I want to from this free body diagram, I am not anything calculate along the x directions. Let it be, but it is told it is having some velocity along that directions. As velocity along inclined down direction, that's why this force was like this. Okay. Now what is the work done for 1 and 2? Okay. So to calculate that work done 1 and 2, what we have to do? This along these directions, if it is W is the force, so and this is W, I should write this way. U12 equal to W sine 15 degree. That component multiplied by displacement is 10 meter minus friction, or somebody can write this way, leave it. Net force W sin alpha here minus mu Kn, this is the net force, downward directions, multiplied by 10. And interestingly, this value is negative. Actually, W sin alpha, I should write this one, 151.9 joule. Okay, W sin alpha value is lower than the mu Kn. Okay, then how it is moving down? Any guess? W, see, this is negative means W sin alpha is lower than mu Km. How it is moving?
Velocity.
Velocity, very good. So if there is no velocity, then it should not slide down, correct? It should not slide down due to the velocity,
Yes, sir.
due to the velocity downward direction. That means due to the kinetic energy, due to the kinetic energy of that particle. But you have to make sure it is downward direction. If it's supposed to these directions, it should not come down, is not it? Although this kinetic energy half mv square, positive, negative, it is with the square terms. But if velocity is supposed to be this direction, it should not move down, is not it? Or
Yes,
it should
yes, sir.
move down. It should,
Yes, sir. It should go upward.
go upward. Very good. So you got that this is the work done. Now, using the work energy principle, using the work energy principle, so what you can do this way, U12, it is moving from this to this, equal to T2 my sorry KE2 minus KE1. You can write this way. Or maybe you can write directly T1 plus U12 equal to T2. Whatever the way you are comfortable, you write that. Okay. So basically, this is also good idea that final positions KE2, kinetic energy 2 will be kinetic energy 1 plus work done. It is better idea that here the total kinetic energy will be, here total kinetic energy will be kinetic energy 1 plus work done. See, this work done is negative because this value is negative. That's why here kinetic energy will be less. You assume there is no friction or friction coefficient 0.3, let it be 0.01. Then when it will move from that to this zone, okay, this zone, this value, this net value will be positive instead of negative. This value will be positive. Then there will be some gain of the velocity, but it is not happening in this problem. Don't be confused with the concept. Concept is always same. What is happening as this mg sin theta, w sin alpha value is lower than the friction force, and your velocity is pushing it to slide down. So this negative work done, this is negative work done will be adjusted with initial kinetic energy. Then you will get the final kinetic energy, and you can see final kinetic energy is 3.15 meter per second. Here it was 4 meter per second. Here it is 3.15 meter per second. By seeing these two values, somebody can confused that body, that 50 kg crate that has moved from A to B. So there will be some height. Okay, it is having some height here, some height. If it is h, so mg is that amount of the potential energy, it is exhausted. So velocity is supposed to be higher than the 4 meter per second square. No, because friction force you have to adjust. If you subtract the friction force, okay, if you subtract the friction force, then you can see no, the friction force is higher value than the potential energy it will give, it will get for height of h. Height of h. Okay, is it clear this problem?
Yes, sir.
Okay, next. As I told, potential energy. I am not adding anything. Here it has been shown in Vg, but you can write PE, potential energy. I am okay for that. whatever is okay. P or Vg. Here potential energy actually due to gravitational force, that's why it is Vg. Okay. G stands for gravitational force. When one particle is moving along the gravitational force, it is positive. When it is moving opposite, it is negative. And Vg equal to mgh. So H has been calculated from the data. Okay, where Vg has been considered as a 0. Now you can see this problem, if you move this to this point, okay, move from this to this point, then what will be potential energy gain? That will be mgh. Okay, mg delta h. Okay, now potential energy, as I told, when it is been stored in the kinetic energy, potential energy, elastic energy for the spring, half kx square, that is stored in the spring. We write potential energy stored in the spring, that is positive. Potential energy stored in the spring, that is positive, and that is elastic. Elastic potential energy, VE, elastic, that is positive. What is stored in the spring, that is positive. But what is the work done? We are telling that time it was negative. Although both are expression was half kx square. One is positive. Why? I'll tell you. Potential energy half kx square. We have learned there that work done was negative, minus half kx square, because if we are not doing anything externally, then it will be 0. When you have spring, okay, so maybe this is the initial conditions, you have moved by x, this is the k. If it is happening that we are not doing externally anything for extension or compression, then potential energy due to this x movement, displacement, that is positive. But work done by the spring, okay, for this one, that is negative. So as a whole, total will be 0. Have you understood this point? Work done was negative, but potential energy stored in the body was positive, because potential energy and work done both are summation wise, it is 0. Have you understood this point?
Yes, sir.
Okay.
Yes, sir.
Yes, sir.
So, and change in your elastic energy potential is this. So it is positive. Stored energy stored in the spring is positive. Work done by the spring, okay, that is negative. Total as a whole, it is 0. Net change is 0. Now work done equations. This is work done. So it is T was kinetic energy, and this is potential energy. Potential energy may have two parts. Potential energy is having two parts. One is due to gravity, and not two parts. One is gravitational, other is like elastic potential energy. Okay, one is gravitational potential energy, other is elastic potential energy. Two parts. Okay, this is gravity, or we write Vg and Ve. Vg and Ve. So work done will be kinetic energy plus change in kinetic energy plus change in potential energy. We can write this way. If this is the system, you have supplied some work done. Say you want to externally work, you have supplied some work done, that is positive. That will do two things. One thing, it will change the kinetic energy. Other is it will change the potential energy. Potential energy may be two ways. One is gravitational, other is elastic. That one has been written here. T1, V1. T is kinetic energy, V is potential energy, and U1, work done, will be T2. T2 is kinetic energy and V2 is potential energy. Okay, or potential energy or work done will be change in kinetic energy plus change in potential energy, or whatever the old fashion you can recall, that is also fine for me. Step 1, step 2. Okay. Now say one example given that this is the one complicated path. Okay. And this is the one scenario. Force are acting F1, F2. And this is the spring. One way we can do to calculate the work done is draw the free body diagram. This is W is acting, this M, G. So there will be some reaction force. So this is the reaction force here. But you can be carefully noted. This is a T directions. This is the N directions. Normal directions will be reaction force. That will not do any work. Normal directions will be reaction force. That will not do any work. So work done will be done by F1, F2, mg, and this K F equal to Kx spring. F equal to Kx spring. Spring I have shown this way. Why? Because it is in opposite directions. Okay. Spring, it is movement is this direction. So spring will try to bring it back to the original conditions. Now, if you this is the real scenario. If you want to solve this issue, is you have to calculate mg, directions F1, F2, Kx. But another option may be, let's have that these positions, it is Vg equal to 0, this is Vg equal to mgh due to height h. Now work done will be change in kinetic energy and change in potential energy. So if you know the velocity, initial and final velocity of the spring, okay, then kinetic energy can be calculated. If there is no kinetic energy, then it will be only potential energy. If there is no velocity of the spring at the final conditions, then it is only potential energy. Somebody can calculate only vertical displacement enhancement or extension or compression, H positive or negative, then work done can be calculated easily. You don't need to bother about value of F1, F2, spring force, mg, nothing. You just calculate the current scenario, what is the height, this h is the height, so mgh is the potential energy gain, okay, from the initial to new conditions, and say let's kinetic energy change velocity v1 and v2, you know, then you can change the work done. So that could be, this could be simple method. This could be simple method to solve. Okay. That one is told that this is kinetic energy, this is potential energy, kinetic energy plus potential energy equal to constant when there is no external force. When there is no work done, externally there is no work done, then this and this should be constant. This and this should be constant. Then somebody can write E1 equal to E2. And this E1, E basically T kinetic energy plus potential energy, total mechanical energy of the particle. And it's at a spring. So this problem at a spring. Okay. Now when E is constant, we can see that transfer of energy between kinetic energy and potential energy can take place. As long as total mechanical energy T plus V, kinetic energy plus potential energy, will not change. This is the law of conservation of dynamical energy. Okay, this is the energy conservation. Now take one example here. I think this is the last. Yeah. Okay. So there is one slider. Mass of the slider is given 6 pound, and it is released from rest. Zero equal to 0 from the position 1, and it slides with negligible frictions, mu equal to 0 in a vertical plane. Vertical plane means this is the x plane, xy plane. Okay, don't confuse it with a straight line. It is 2D problems, xy plane. Okay, along the circular rod. So circular rod means this is 24 inch. If it is 24 inch this to this, this to this, up to this, 1/4 portion, it is circular arc, 24-inch length. And spring has attached with the stiffness of the spring K, 2 pound per inch. Spring stiffness is given. Determine the velocity of the slider when it is at the position 2. V2 you have to calculate. Okay. So somebody can try this way, that work done by the weight and the spring, the work done by the weight and the spring force on the slider will be treated as the potential energy method. We will use potential energy method. Okay. So reactions of the rod on the slider is normal to the motions and which will not do any work. So U12 will be 0. So U12 will be 0. Now we have to consider some datum. Okay, let's have this is the datum. This is the datum at 1. So at 1, if it is the datum, okay, at position 1, gravitational potential energy Vg at 1 it is 0. At 2 it is mgh. At 2 it is mgh. Okay, here it is datum. If this is the datum, h is negative. Datum is this. Try to understand. Then m is 6, g, let it be everything unit, foot, pound. Let it be pound. So m will consider this as the m directly, pound, not poundal. Pound. G is 24. Sorry, as it is m is pound. We will have everything foot pound. Then G will not consider. Okay, and h is 24 inch, 24 by 12 foot. So it is this value. Now initial velocity here. Initial velocity
0.
it was 0, and final velocity you have to calculate, is not it? Okay, fine. So initially, what is the spring kinetic energy? Sorry, potential energy. Potential energy of the spring for this half k x1 square. This is the x1 square.
Yes, sir.
Okay. Now, as the spring says, is it told it is having some unstressed length is 24 mm. So this was the unstressed conditions. So x1 is 24. This to this, is not it? For 1, this is this much it is been stressed 24 inch, is not it? This is the unstressed conditions. But for 1, it is been stressed by this 24 inch. So x1 equal to 24 inch. For x2, how much? What is this length? We have to calculate. Okay. Now to calculate this length, you can see this is 24. This is also 24. What is this length? This length
24
x2.
root 2.
Yes. Square root 24 square plus 24 square. So x2 equal to 24 square root 2 inch. Now,
Sir, 24 root 2 minus 24 x2.
Okay, sorry. Yes. This is the length. Then it changes minus 24. Yes, very good. Thank you. Now, V potential energy for 1, half k x square, half k is 2 pound per inch. K equal to 2 pound per inch. 2 multiplied by 12 pound per feet. So that's why multiplied by 12. X square 24 inch by 12 feet square, this much. V2 half 2 12 x square, this one. Now you come here, that this is kinetic energy. Just a minute. This is T1 is kinetic energy at 1, V1 potential energy at 1. This is the work done. T2 kinetic energy at 2, V2 is the potential energy. Just a minute. So initially kinetic energy 0, potential energy, work done. This is kinetic energy at 2. Just a minute. Okay. Now this is 0.48, 0. Then this is the kinetic energy, and this one. This is kinetic energy. This one Vg, and this one Pg 12, correct? Let me check from where this has come. This is
Me too.
potential energy. Yes, potential energy. No, in other term I can write here V2. Yes, you are right, V2. So let it be then V2. One is Vg, other is V2. Yes. So potential energy, one is gravitational, other is stored energy, stored elastic VE basically, elastic energy stored. So now you use properly with proper sign, you will get the values. That's all. Let me show you the problem sheet. This one. Okay. Number 1, there is one spring unstressed conditions x equal to 0. If the body moves from the initial conditions to x2 equal to 200 millimeter, so this is x equal to 0 and x equal to 200 millimeter, determine the work done by the spring on the body, work done by the spring on the body, and the determine the work done on the body by its self weight. Okay. So first of all, work done by the spring. But the spring, I told that spring, the displacement is one directions, force is acting in other directions. So in that case, that U12 will be negative. Negative K, negative half K x2 square minus x1 square minus half K is 4 kilonewton per meter, 4 multiplied by 1000 Newton per meter multiplied by, so this problem told that x1 is this, x2 is 200. So
0.2 square.
yeah, directly I can write 0.2 square minus 0.1 square. It is minus 16 Newton per meter, 16 joule. Now what is the work done by the body? Work done on the body by its weight. Weight is acting in downward directions and displacement is also downward directions. So in that case it is positive. U12 prime equal to positive mg y1 minus y2. Or somebody can say this way, this is the length, this is the length, this length is 200 minus 100 mm, and this is 20 degrees, so this is height will be 100 by 1000 sine 20 degree, that meter. Okay, so this is the difference. You put the value, you will get this joule. Done. Now there is a 10 kg block that is released from rest on a small collar of mass m, and it slides along the curved path. Express the velocity of the collar, okay, when it strikes the base. So there is no friction. If I add the friction you have to consider, or else U12 will be delta T equal to mgh, okay. Equal to half m v square minus 0 square. Simply we will get these equations. That you can write v equal to square root 2gh because there is no friction here, okay. Number 3, there is a 6 kg collar, cylindrical collar that is released from rest, v equal to 0, v0 0, m 6 kg. Calculate the velocity v of the collar when the spring has compressed by 50 mm. This spring, this collar will hit here and it is compressed by, finally it will compress by 50 mm. It will compress by 50 mm, okay. If in that condition, if somebody want to draw the free body diagram, one is this 6 multiplied 9.81 and it is K 12 multiplied by 1000 Newton per meter, Newton per meter multiplied by x. This is a general criteria for this. Now, if somebody want to calculate this, can consider this is the datum. This is the datum, final datum, that is just a 0, and it is from the top, so it is moving 500 plus 50, 550 mm. So somebody can utilize this way. Directly I am giving hints. Mg is equal to half m v square plus half k x square. See, this mg is from here, this to this, that much work done. Sorry, you can say that much work done. You consider mg as the work done here. That much work done will be total work done. Then velocity it will possess v. Then half mv square will be its kinetic energy. Initially it was 0, and other energy will be potential energy on the spring, half kx square. That means m, what is the m value? 6 multiplied by 9.81 multiplied by 550 by 1000 MGA is equal to half multiplied by 6 multiplied by V square minus, no, plus half K is 12,000. What is X? What is the X value?
50 millimeter.
50.
50 by 1000 squared. Okay, you solve this, you will get the velocity 2.41 meter per second. How much? Oh, it will supposed to be 6. Okay. Now this problem, there is a nest of two springs that is used to bring 5.5 kg plunger. This is 0.5 kg plunger A to a stop from the speed of 5 meter per second and reserve its direction of motions. The nest of two spring is used. There is a nest of two spring. One is here, other is this. Is used to bring the 0.5 kg plunger A to a stop from a velocity of 5 meter per second. And here finally it will be 0 velocity. And it is the some glide through which it can travel in horizontal directions. The inner spring increases decelerations. Initially this will hit and it will be contact with the outer spring. Then it will move by distance s, then it will touch this one, inner spring. Further it will decelerate. And the adjustment of its position is used to control the exact position at which the reversal will take place. Which location reversal will take place? If this point is to be correspond to a maximum deflection delta equal to 200 millimeter of the outer spring, specify the adjustment of the inner spring S. So initially this will hit outer spring, that will move by S, then the inner spring will be in contact. Finally, maximum value of the displacement of the outer spring will be delta 200 millimeter. Okay, where velocity will be 0. Then you have to calculate the value of S when the outer spring, say maybe K1, 300 Newton per meter, inner spring is 150 Newton per meter. Many ways this problem can be solved. One way it can be, initially velocity was 5, finally it is 0. So change in kinetic energy equal to change in potential energy. I can utilize this way. Change in kinetic energy is half m v square minus 0. Change in kinetic energy is half k1 300 multiplied by delta square. This is 0.2 square plus half multiplied by 150 multiplied by 0.2 minus s square. You calculate this, you will get the s value directly, 142.3 millimeter. Or you can have second options. Say this is f and this is x. So initially it will move like this, distance s. Okay. Then second one will be in contact and its slope will be little high and it will move further distance. And this is 0, this distance is delta equal to 0.2 meter. Now this one is f1 and this is f2. This is k1, this is k2. Basically here k2 prime. Here this k2 prime will be k1 plus k2. From this, what will happen? Up to this it was K1 stiffness, but when the inner one is connected, then K1 prime will be K1 plus K2. If somebody can calculate this area, this one, then this one, then this one, A1, A2, A3, this three area, if somebody can calculate, then finally we will get the value of S from the expression. Because that area will be same as half mv square. Okay, that area will be same as half mv square. The same thing we can directly write this way. This is half mv square equal to this and this. Because outer spring will move delta distance, inner spring will move delta minus s distance. That's all. Okay. Next question. The one force P 40 Newton is applied to the system which is initially at rest. This one. B equal to 0. Something is told already. P equal to 40 Newton. Okay, determine the speed of A and B after A has moved by 0.4 meter. A, this has moved by load you have applied here. So this is the displacement, some VA, that direction, this will be VB. This point is finally moved to delta equal to 0.4 meter. Okay. So P, due to P load, work done. What will be the work done? W or U12, what will be work done? 40 multiplied by 0.2 joule.
Sir,
Here,
A has moved 0.4 meters.
oh, sorry. A has moved 0.1. Sorry, very good. So this one we don't know. A has moved, yes. A has moved 0. Maybe this one, delta. This delta equal to 0. Thank you. Okay, meter. Fine. Now, if I consider this one, SA, and this is SB, so 2SA plus SB plus constant, that is the length, is not it? Total length,
Yes, sir.
or VA plus 2VA plus VB equal to 0, or VB equal to minus 2VA. Okay. Now, due to P load, B has to move right. Correct? Positive x. So this is y. Positive x. Then A will move in negative x. Is not it? This sign is indicating same. One is positive, other is negative. Okay. Now, same time, if A move by 0.4 meter, B will move how much? If SA equal to 0.4 meter, then
0.8.
SB will be 0.8 meter. So this work done will be 0.8, 32 joule. Okay. Okay. Now That we understood that much of joule it has moved. Now, if I use two conditions, that initially it was at rest. Initially it was at rest. So, kinetic energy plus work done equal to kinetic energy at T0 equal to kinetic energy at T equal to T. There is no potential energy because there is no vertical direction movement. Is not it?
Yes, sir.
Initially it was 0, 0 equal to half, sorry, 0 equal to 32 equal to kinetic energy at the final stage half m, sorry, half multiplied by 6 multiplied by VA square plus half multiplied by 10 multiplied by VB square. VA equal to VB equal to minus 2 VA. You put here, then you will get VA. 1.18 meter per second left, towards left. VB equal to 2.36 towards right. That's all. Okay. That I have solved. Now last one. A car of mass m, this is the mass of m, so it is mg, accelerate on a level road, no inclinations, under the action of the driving force F with the speed, so there is force F, v1 to speed v2 for distance s. If the engine develops a constant power equal to P, the constant power output P determine V2. Treat the car as a particle under the action of single horizontal force. So 1D problem. Single horizontal force. So it is simply, we can write the expression for power equal to force multiplied by velocity. P equal to F multiplied by V. F equal to ma, then V. Acceleration equal to P by mv. It is told P is constant. P is constant. Okay. P is constant. Acceleration is nothing but V dv. If I write this expression, V dv equal to A ds. This expression I want to utilize A equal to P by mv ds. V dv equal to P by mv ds. V square dv, mv square dv equal to P ds. Take the integration v1 to v2, P is constant, so 0 to s. It has started from rest. So I consider distance traveled is s basically. You can write s1 to s2 and that one will write as a s equal to m v cube by 3 v1 to v2 ps s1 to s2 m by 3 v2 cube minus v1 cube p s2 minus s1, that is nothing but s. Then v2 cube minus v1 cube equal to 3 ps by m V2 equal to 3 PS by M plus V1 cube power 1 by 3. Okay, that is the answer. Done. Okay. Now, can you tell me what are the problems you are facing at that time? Last day, what are the chapters I have covered? I think which chapters? Let me check. Last day, dynamics 11 and 7. Anybody is having any issue from that problem sheet 11 and 7? This is the 11. Any issue do you have from the chapter 11? No, correct? Okay. Then chapter 7. This one. Any issue? We can discuss. Chapter 7. Okay, this is not required. Okay, fine. Then I can take attendance. Just a minute. So as per the plan, next day will be class test. I have posted also. Syllabus will be kinematics. So problem sheet dynamics, problem sheet 1, 2, 3 and 5. There will be 4 problems. You have to answer any 3. Okay. So question can be new, can be from problem sheet with data change, anything can happen. Now quickly attendance, just for within 1 minute. Just hold on. Okay. For aerospace, 25, 26, 27, 28, 29, 30. Present. Civil 77 present, 78 absent, 79, 80, 81 absent, 80 is present, 81 absent, 82, 83, 84, 85, 86, 87, 88, 90, 91 present, 91 present, then 92 absent, 93 absent, 94 present, 95 present. Then CST 58 absent, just a minute, 58 absent, 59 absent, 60 absent, 61 absent, 62 present, 63 absent, 64, 65, 66, 67, 68, 69 present, 70 absent. Electrical 49, 50 present, 51 absent, 52, 53, 54, 55 present, 56 absent, 57 present, 58 present, 59 present. Then electronics 35, 36, 37, 38, 39, 40, up to 40 present, 41 absent, 42 absent. Then IT 53 absent, 54, 55, 56, 57, 50, 53 present. Okay, 53 present. Now IT 53, 54, 55, 56, 57, 58, up to 58, everybody present. 59 is absent, 60 is absent, 61 present, 62 absent, 63 present, 64 present, mechanical 50 is absent.
Sir, 50 present.
Sorry, 14, 49 is absent, 50 present, 50, 51 is present, 52 absent, 53 absent, 54, 55, 56, 57, 58, 59, 60 is absent. Then metallurgy 25, 26, 27, 28, 29 present, 30 absent. Mining 25 present, 26 absent, 27 present, 28 present, 29 present. Sorry, 29 is absent. Okay, just a minute. Those who are absent, once again, civil 81, then CST 58, 59, 60, 61. Then CST 70 is absent, electrical 51 absent, 56 absent. Then electronics 42 absent. Then IT 59 absent, 60 absent. Then IT 62 absent. Then mechanical 52 absent, 53 absent. Mechanical 60 absent. Then yes, 60, mechanical 60. Mechanical 60, just a minute, mechanical 60 present. Okay. Then mining 26 absent, mining 29 absent. That's all. Okay, guys, thank you. See you next day for a
Hello,
meet.
sir. Hello,
Yes,
sir.
yes.
Sir, I think 62%, sir. I was
1 minute.
waiting.
1 minute. IT 62. Yes, given. Okay.
Yes.
Okay, next day, what will you
Hello,
be?
sir.
Yes, tell me.
Sir, I have a genuine problem. Can I,
Yes, what problem?
sir?
Shubhankar.
Sir, if the mass is changed, sir, can then the uh, theory is applicable?
No. Mass is not changing. We are assuming. Okay. The, the, the,
Yes, sir.
the
But if changing,
then appropriate equations you have to use. If mass is, we are not going into that level. Okay.
okay, sir.
This is very preliminary dynamics.
Okay, sir.
Okay. Very basic dynamics we are covering. No
Okay, sir.
change of mass. Right?
Yes, sir. I think
Yes.
about sir rocket, sir. So I
No. We were not going
thank you,
that
sir.
one. It is very preliminary dynamics. Statics, we are little bit advanced. So nothing is new in statics. But dynamics, this is the beginning. Okay.
Okay, sir. Thank
Okay,
you.
fine. So next day, be on time. So I'll take the class test as per the scheduled time. 45. I have written there. No. Then I will show you the answer script of the mid semester exam. Okay. So be ready with that. So once exam is over, I will post the slot also. Just because within after 1 hour that class test, I have another 1 hour. Within that, I have to finish. So be present. So first of all, you have to give the class test for kinematics. Then I can show you the answer script. Okay, guys. Thanks for your patience. Okay. Bye.
Thank you, sir.
Thank you, sir.
Thank you,
Thank
sir.
you, sir.